microcontrollers versus microprocessors. There is a fundamentally huge difference between microcontrollers, MCUs, and microprocessors, MPUs. There is a fundamentally huge difference between microcontrollers, MCUs, and microprocessors, MPUs. However, there are many of who are still confuse these terms. So let's put it in perspective. The chip on the left is a microcontroller. It's an Atmega16 from Atmel. This single chip has a built-in CPU, RAM, ROM, I/O ports, serial ports, SPI, I2C, and UART. Number 3, timers and many other peripherals. It's a single chip full computer on which you can flash and run your code and also take advantage of all the built-in peripherals. The chip on the right is a Zilog Z80 microprocessor. It's an old microprocessor released back in 1976. This is a bare processor that needs a RAM, ROM, and interfaces to do any computing job as any microcontroller out there. Now I will connect some peripherals to my Z80 MPU, such as a dynamic RAM, ROM, ADC, DAC, and input-output controller as shown in the image below. I'll read that last sentence again. Now I will connect some peripherals to my Z80 MPU, such as a dynamic RAM, ROM, ADC, DAC, and an input-output controller, as shown in the image below. Now we're talking. A microprocessor is connected to a RAM and ROM, which means that we can load a program for it to execute. It's also connected to an ADC, DAC, and input-output controller, which means that it's capable of doing some basic input-output operations. But is it really comparable to a microcontroller? Nope. Maybe after connecting the peripherals, as shown above, we can compare the MPU with its externally connected peripherals with an MCU, which will still be way ahead of the MPU. The MCU still has more peripherals, ports, and features than the few external ones which we added to the MPU. I'll read that last sentence. The MCU still has more peripherals, ports, and features than the few external ones which we added to the MPU. The bottom line: a microcontroller is typically a smaller version of a computer which has a microprocessor at its own CPU, with internal RAM or as its own CPU. A microcontroller is typically a smaller version of a computer which has a microprocessor as its own CPU, with internal RAM, ROM, and a bunch of peripherals. It's a full computer system on a single chip. While a microprocessor is single chip CPU that cannot do anything without connecting some external hardware to create a computer system. Fundamental terminologies. You should be familiar with the following fundamental terminologies. As a beginner in microcontroller programming, it's absolutely substantial to understand all of the following terminologies. Read them carefully and mark the ones you cannot grasp right now. At the end of this tutorial, you'll be sent again to read these definitions again. Then everything should be clear. If not, please use your search engine to find out what do these terms actually mean. Program. A set of instructions for a computer written in a programming language. which implements an algorithm, finally assembled in assembly instructions that are coded and flashed to the memory in form of zeros and ones. Paging. A page is a logical block of memory. A paged memory system uses a page address and a displacement address to refer to a specific memory location. Bank. A logical unit of memory which is hardware dependent. The size of a bank is further determined by the number of bits in a column and a row per chip multiplied by the number of chips in a bank. Pointer. An address of a specific object in memory which is used to refer to that object. Stack. The hardware stack is a section of memory which is used to store temporary data or registers values. A software stack is a last-in, first-out data structure which contains information that is saved, pushed, and restored. Popped. Stack pointer. A register which contains the address of the top of the hardware stack. Program counter. Abbreviated and well known as the PIC. It's a register which holds the address of the next instruction to be executed. The program counter is incremented after each instruction is fetched. It's incremented once / instruction cycle. Interrupts. An interrupt is an event that suspends the main program execution while the event is handled by another program. Interrupts substantially increase the system's response speed to external events. Interrupt vector. The location from which the program continues execution. The location interrupt vector is usually passed over during regular program execution. Clock. This is the beating heart of a microcontroller. It's fixed frequency signal that triggers or synchronizes CPU operation and events. A clock has a frequency which describes its rate of oscillation in megahertz. The clock source could be an external RC network, crystal oscillator, resonator, or even a built-in internal clock source. The frequency of oscillation is usually referred to as frequency oscillation. Machine cycle. The machine cycle is the time it takes the system's clock to repeat itself. For a microcontroller that has a 4 MHz crystal oscillator hooked to its clock input pins, the machine cycle will be 1/that, which equals 250 nanoseconds. Instruction cycle. The instruction cycle is the time it takes a microcontroller to complete the execution of a single instruction. This includes fetching, decoding, execution, and saving the result, which takes 4 clock cycles for the MCU we'll be using. So 1 instruction cycle equals 4 machine cycles. And we can also say that a CPU is running at 4 MHz, executes frequency oscillation divided by 4 instruction per second equals 1 MIPS, million instructions per second. Cross development. We'll be programming MCUs during these tutorials, as you should expect. But what kind of development is this said to be? Well, when you're coding on your PC to create applications that also run on PCs, this is said to be development process. However, it's not always the case. In many situations, you'll be writing code on a specific machine, example your PC, which will eventually get compiled to a machine code that runs on another machine, example Android, iOS, MCUs, etc. This is what we call cross-development. and this is the case for embedded firmware programming. Note, a compiler used for cross-development is often called a cross-compiler. Language to use. Which language to use? There are actually many available programming languages to use for developing embedded software. However, the C programming language is the standard in this industry. It has been and still considered as the most efficient way to interact with the low-level hardware at the register level. Most of the advanced high-volume quality products are developed in C. We may mention assembly at some points. It's been known for too long that you can do more optimizations in your system with the assembly language, and that's true, but use it for learning purposes only at this phase. Otherwise, you'll be wasting too much time without gaining profitable skills. As every processor has its own instructions, consequently, it has its own assembly commands, so it'll only be an educational practice. However, you are not restricted to the others' choices. Everybody has his own preferences, so I encourage you to use the language you're familiar with, if it's available for the device family which you're using. The compiler XC8. The programming language in which we'll be writing firmware to the PIC MCU is called the C language, the standard ANSI C, which has been the most efficient option for embedded software development during the past few decades, and still proves to be the best fit for writing firmware up until today. And please be advised that this course is built upon the assumption of your familiarity with basic concepts in C language. However, all code listings are written to be newbie-friendly while maintaining the overall efficiency levels as high as possible. Almost all industrial machines, military fighters, rockets, compilers, and even other programming languages all are built in C. With this fact in mind, you should appreciate the effort and time it takes a person to be good at this language. Just practice it as much as you can. It's the key to mastery in almost every field of knowledge. The C compiler we'll be using is called XC8 from Microchip for 8-bit MCUs. You can download the suitable version for your operating system from this link. Download XC8 compiler. Setting up the compiler is also a straightforward process which you can easily do it yourself. Or you can follow the steps in the next tutorial for installing both MPLAB IDE and XC8 compiler. Well, I'm a little bit hesitant to read software installation instructions, especially when it doesn't have pictures. I'm not being critical, but I will in fact read it because I don't want to miss anything, and I'll try and leave timestamps below so that in future somebody watching this, or maybe myself, can just skip ahead. But I will go through the painful process of reading this all. IDE MPLAB X. Forgive my attitude. I have a good attitude. Don't worry. The Integrated Development Environment is the software platform on which we'll be developing our projects. This is a computer software that gathers a bunch of tools which eliminates the overhead of less important tasks, which helps developers focus their attention on the whole systems and spot their major problems that need more investigation. It's kind of wordy. The IDE which we'll be using for this course tutorials is called MPLAB X from the Microchip Incorporation itself, the same manufacturer of PIC microcontrollers. It's the official option, yet the most powerful one out there. It has too many great features which may possibly cause you a little bit of frustration. No need to worry anyway. Very soon, maybe very quickly, you can download the suitable version for your operating system, Windows, Linux, and Mac, through this link down below. Download the MPLAB IDE. Other options of IDEs are some pirated, cracked software, or drag-drop Arduino-like environments. This is based on what I've experienced myself. Maybe there is a worthy choice that I wasn't lucky enough to find. All in all, the official MPLAB IDE is more than enough for our course in the meantime. For installation, you can follow the video down below in compilers section. However, you don't actually have to. Installing MPLAB is kind of a straightforward process that sounds like next, next, yes, finish. One thing to notice is that you must install the MPLAB IDE at first before installing the compiler to avoid integration issues between both of them. That's important to note. Maybe I can timestamp that. Note, despite the fact that IDEs are created to be very useful and efficient tools, the other face of the coin is that it gave us enough luxury to abandon all discipline at some points and tweak things here and there, hopefully until a solution is successful. At the end of the day, we ended up having too many engineers with limited experience in the estimation of systems behavior under certain circumstances. Be careful. I think this means microcontroller. How does a microcontroller run a program? Now we're about to discuss how an embedded program runs on a typical microcontroller in technical terms. First of all, the program should be loaded into the microcontroller's program memory, ROM. After writing the code in C, the compiler and assembler will generate a hex file that you should burn flash to the microcontroller chip thereafter. The program instructions be a bunch of zeros and ones, obviously. Next, the chip must be powered up as any electronic device. Typical microcontrollers run at 3.3 or 5 volts DC. We should also connect the crystal oscillator to provide the chip with the clock input. Now the microcontroller will start executing the instructions stored in memory sequentially. Each instruction execution takes up to 4 clock cycles, which work as follows. An instruction is fetched by the CPU from the program memory, and the program counter PC gets incremented to point at the next instruction in the program memory. The fetched instruction, this is number 2. Number 2, the fetched instruction will be decoded in the second clock cycle. Number 3, the instruction operation is performed, executed. It could be add, sub, mov, div, or whatever. The execution happens during the third clock cycle. Finally, the result gets saved to the working register in the fourth cycle, which was the final step in executing the first program instruction. Now the PC is pointing to the second instruction as you've seen in step 1, and everything is repeated over and over again forever or until the power goes off. Q1, latch in fetched instruction increment PC. Q2, maybe these are the clock cycles. Input register data load. Q3, operation. Q4, result save. So this is the instruction cycle. which obviously explains why a machine equals a quarter instruction cycle, or in other words, the MCU is said to perform frequency oscillation per 4 MIPS. Next category, computer simulation. Using computer simulation software can substantially improve your learning experience with multiple embedded systems platforms, example ARM, AVR, PIC, etc. However, a typical simulation software, example Proteus, will only catch you logical code errors, even though it's still a powerful tool that helps you avoid flashing and testing firmware on real hardware, as long as we can easily prove this firmware won't run correctly or won't give the expected results. With only a few clicks, a drag-drop, you'll have your schematics fully connected and ready for some testing. You can use whichever simulator you prefer. I'd strongly recommend Proteus for most of the beginners, and you can check their website to find a student version or whatever suits your budget. Pro tip: if your code is running flawlessly in the simulator with 0% error, that's not a complete sentence. If your code is running flawlessly in the simulator with 0% error, there is still no guarantee that it'll run seamlessly in real-life settings on a real prototyping board. Any MCU-based kind of system could possibly go really insane, just because of tiny hardware issues. These issues are impossible to be predicted by any means of computer simulation. Development Hardware Kit. A typical course in embedded systems is practical in nature, hence the importance of getting a decent hardware kit to play with. The list down below includes all the necessary parts and components needed for the practical labs in the upcoming tutorials. We can also categorize these components into two categories: basic kit and extra modules. The first one is everything you must have in order to follow up these tutorials and create all the basic projects yourself in a real-world sense. The latter list has some extra modules for larger budget beginners, which helps you complete almost all of the tutorials covered herein or create whatever project you'd like to develop at your own pace. The basic course kit, essentials. Extra modules for advanced tutorials, optional. Check out the specific components, parts names, and quantities in the course kit resource page. I guess I know that I could click on that, but just a quick look. Breadboard, a PIC chip, a PIC2 programmer or a PIC3, a bunch of LEDs, resistors, potentiometers, different values, a push button, a battery, 9-volt battery clip, a 5-volt regulator, crystal oscillators, 4 MHz, 8 MHz, 16 and 20, 7-segment display, okay, 5-pin male-female cable, ultrasonic sensor, LDR, relay, unipolar stepper motor, DC motor, Bluetooth module, a motor driver, don't know what that is, and jumper wires. Pretty basic stuff. That's not a comment, that's just... okay. Alrighty, the next section is prototyping board. In embedded systems practice, you must be working with various hardware parts, and especially microcontrollers, which introduces the following issues. Programming the microcontrollers in a generic way involves removing them from breadboard and mounting it on the programmer's circuitry. When the firmware is flashed to the MCU, then you take it back to the breadboard, testing environment, as you may have noticed that updating the firmware involves removing and reconnecting the MCU from the breadboard, which will possibly damage your MCU and result in some bent and broken pins. Number 2, if your MCUs typically operates at 3.3 or 5. MCUs typically operate at 3.3 volts or 5 volts, which requires that you've got your own power supply and voltage regulation on board in order to guarantee the operating power required specs. For these reasons above, we'll stick to a fixed onboard development connection, which means that you'll have to construct the basic circuit down below only once. Then you'll be able to easily test your projects on board. This connection has the following features: onboard ICSP, in-circuit serial program report, which means you can easily flash the chip without being removed from the breadboard. Regulated 5-volt power supply connection for powering the chip up with LED indicator. Reset pin is pulled up and hooked to a push button. Oscillator input pins are connected to our crystal oscillator. The final fully connected circuit is shown down below. That's worth pausing and taking a look at. At the end of this tutorial, please double check the terminologies, like the glossary definitions, which you've seen earlier, just to make sure these concepts are now clearer than before. Click the link down below.